and welcome to the webinar on accelerated mechanical system designs with Ansys motion, rigid body dynamics and drivetrain analysis. So in this webinar, we are going to explore, so this is the agenda for today's webinar. So initially, I will give some overview about multi-body dynamics and generally in dynamics, what are the topics that we will be solving in real life examples, like what kind of simulations or what kind of applications generally we deal with dynamics, and for what kind of for what kind of applications, what kind of simulation approach we go through it, and what are the different results that generally we will be extracting from that particular analysis. We will be checking, I will be showcasing few slides on that dynamic analysis. And when it comes to multi-body dynamics, what are different approaches that we generally prefer in ANSYS, and in which kind of multi-body dynamic analysis will be, like for which kind of multi-body dynamics, which kind of solver we prefer to go with. And in the multi-body dynamics, what are the different connections we can consider, like different type of joints and contacts. Okay. And so we'll give a live demonstration of one of the rigid body dynamics, considering all the parts as rigid bodies. And in ANSYS motion, we have advantage of creating the geometries or connections between the geometries by using the different toolkits. So I will showcase one demo on Drivetrain toolkit setup. Generally, in case if you don't want to work much on the CAD, if you want to take the advantage of the Drivetrain toolkit to create any geometries like gears, shafts, or something, how we will be doing that. So I will showcase that one as well. And at the end of the session, we will discuss in case if you have any queries or something like that. In meantime, also you can keep your question in the chat box in case if you want to. Uh, if you have any queries, you can keep your questions also in the chat box. Okay. So let's start with some introduction to multi-body, like overall dynamics, and especially focusing more on the multi-body dynamics. Okay. So as we know that over the period of time, like when we talk about any technology, like if you take aerospace or automotive or any aerospace or defense, any technology that if we consider, so every decade the complexity of the mechanisms are increasing, the number of parts are increasing, and now we will be considering multiple mechanisms for all designs. Okay, and along with the designs, the way we will be checking the results or what type of materials we will be using and what kind of different loadings that we will be using. So the design complexity and integration with multiple loads and boundary conditions with different materials. So the complexity is increasing every year over the period of time. And as we know that as the complexity will increase, to design the mechanisms or the parts that we will be using for the mechanisms will be also a bit complex. So this is the general, system-centric approach that we'll be following to design any component or assembly. So initially, first we'll analyze what is the purpose of the uh, mechanism that is going to perform, and based upon that, we will be having some initial design or some early based upon the concept, we will be having some system requirements and early design. And once we have the early design, we may create some CAD model, and we'll implement that. Means we'll go with the one physical prototype, and we will perform different type of testings and training. And based upon the operations that we'll be performing, we'll check. Suppose you have one mechanism, and once you create the prototype, once you do that testing and training, if everything will work, then we will go for the production. If any one of the component will fail, then we will do the modifications in the component. Okay, like sometimes we may change the dimensions of the geometry which is failed, or we will replace the material with a better strength material. Okay, or we will do some modifications in the mechanism to diverse the load. So there will be multiple approaches that we generally proceed as per the failure. So like that, for each and every prototype, if there is any failure, we will be going with multiple redesigns. and finally we'll make sure whatever the design that we have, it will sustain the loads and boundary conditions that particular mechanism is going to withstand. But here the problem is every time we redesign, it will take a lot of time. Like the product development time will increase as we'll be going with the physical prototype, which will be a very time taking one, and along with that, product development cost also will increase. Okay, so instead of this, okay, so instead of going directly with the prototype, there are few like we here in. Okay, so instead of going with the system-centric approach, we can integrate the design into different levels of software in order to reduce the product development time and cost. So one way is the traditional development process. Okay, so where we will be like based upon the problem statement, we will be having the initial design and we will develop that initial design. And after that, we'll create the CAD model. Like once we have the CAD model, instead of directly jumping into the prototype. Okay, so once we create the initial design, instead of directly jumping into the prototype, whatever the loads and boundary conditions that we are going to use at prototype level, so the same loads and boundary conditions we will be applying in the simulation platform. Okay, so here in the simulation platform, like if we face any issue or suppose there is one mechanism we are going to design, in case if the mechanism is locked because of some over constraints, or if the joint loads or if the torque that is required to run the mechanism is too high, then within a few design changes in the software itself. Okay, so we may do some changes in the mechanism, or if any one of the part is going to have high stresses, then we may increase the dimensions of the geometry. Okay. Or we may, if we have a better material, then we will be taking few materials and we will be checking the performance of the mechanism, like what is the performance if we use X material, or what is the performance of the mechanism if we use Y material. So like that, we will be creating multiple designs at the simulation stage. And once we have the best design, so that design might be like you can go with 10 different variations or 20 or 50. So like that, you can create multiple designs and you can pick the best design. And based upon that best design, you can go with the physical prototyping and you can perform the testing and we can validate and build. Like whatever the results that you will be getting from the simulation, you can compare the same results with the physical testing. So once both the results are matched, then you can go with the production. Okay. So this is one way where we will be using the full physics-based simulation, like it is a pure physics-based simulations. So in case if you want to step up and you want to integrate the simulation software with machine learning based optimizations. Okay. So here in the first approach, we will create the design, we will do the modification on our own, and we will be running multiple simulations. So in case if you don't want to run multiple iterations or multiple geometries, if you don't want to go, even we can integrate this simulation with mission learn based optimization. Okay, like suppose you have one geometry, and so by using the mission learn based optimization, by considering the initial dimensions of the geometry, you can create 300 different geometries or 400 different geometries. And so like that, you can create multiple geometries within a few clicks, hundreds of geometries you can create. And for all these hundreds of geometries, you can perform the simulation and by giving some constraints. Okay, so constraints in the sense the maximum allowable stress is some 100 megapascal, or the maximum allowable deformation is 0.2 mm, or the maximum torque should be less than some 10 Newton meter. So like that, you can keep your constraints, and based upon that, you can pick the best design out of 100 samples or 200 samples. And that particular sample only, again, we will go with the physical prototype testing and validate and build. Okay. So this way, compared to this one, again, we can reduce a lot of product development time. And now moving into the era of artificial intelligence, even once we perform the simulation, we can integrate the AI based training and prediction. Okay. So like suppose you have 10 different designs with different results, like each design will be having different loading conditions, and for that loading conditions you have the different stress values, strain values, or how the mechanism is moving, or joint loading conditions are on. Okay. So if you upload 10 different designs with different results, so you no need to perform the simulation. When you upload the 11th design, which is a fresh one and which doesn't have any results, so based upon the AI-based training and prediction, automatically it will analyze the designs of the previous solved problems, and based upon the data, it will map the results and it will give you a result within a fraction of minutes, like in minutes or seconds, based upon the how big your model is. So like that, we can perform the simulation at different levels, like the pure simulation, which is based on the physics-based solvers, or we can integrate the physics-based solvers with machine learning platforms, or even with the artificial intelligence. Okay. So yeah, so when it comes to multibody dynamics is nothing but the analyzing the dynamic behavior of interconnected geometries. That is nothing but if you have more than one component, and these multiple components are connected by different kind of contacts or joints. Okay. And if you want to analyze the response of the assembly, so that is what we will be exploring in this particular session, multibody dynamics mostly focusing. But before that, I will give some overview about the different dynamic analysis that we have. Okay. So in general, whatever the application that we will be solving in structure will fall into two categories. One is static analysis and another one is dynamic analysis. Okay. So static analysis is nothing but whenever we solve any problem or whenever we are working on any project. So if our project or if our assembly is not having any time dependency. Okay. So if there is no time dependency in our problem, if no component is moving with respect to time, or if there is no load variations with respect to time, like, or if there is no sliding, okay. So basically, if there is no time dependency, we will consider that as a static analysis. But whenever there is a time dependency, if any one of the component is moving with respect to time or some variations, or if there is any sliding, so obviously, if it is a time dependency problem, we need to consider the inertia effects as well. Okay. So like that, if we have a time dependency, we will go with the dynamic analysis. If we don't, if our problem statement doesn't vary with respect to time, if it is independent of time, we will go with the static analysis. And similarly, we can solve the problems related to thermal analysis as well. Okay. So this is the equation that we'll be using to solve the problems related to static, and this will be using to solve the problems related to dynamic analysis. So again, dynamic analysis will be having multiple applications. Okay. So mostly like all dynamic analysis will be divided into two things. One is implicit dynamics and another one is explicit dynamics. So in the implicit dynamics, again, we have two things. One is linear dynamics and another one is nonlinear dynamics. Okay. So in terms of applications, if we talk about, generally in structures, we have static analysis and dynamic analysis. And again, in the dynamic analysis, we have different type of vibration analysis. Okay. So because like the kind of vibration analysis also, there will be different types based upon the kind of vibration that our mechanism is going to withstand or it is observing. So again, in the multibody dynamics, like the nonlinear transit dynamics, we have three approaches in Ansys. So I will give an overview about these things. When it comes to dynamics, what are the different vibration analysis that we can perform based upon what kind of applications? And again, in the nonlinear dynamics, nonlinear transient dynamics, we have three approaches. And what is the major difference between these approaches? Okay. So whatever the problem, whatever the dynamic problems that we will be solving, especially when we talk about vibrations. So suppose if we take any motor or if there is any rotating equipment. So one of the major challenge that we will be facing while dealing with the vibrations is if any geometry which is having external vibration. So if there is any external vibrations which will collide with the natural frequency of the vibration, there is a high chance that particular geometry is going to be in resonance condition. Okay. So resonance is nothing but the match of natural frequency with the external frequency. So to predict the natural frequencies and to make sure that natural frequencies will not be colliding with the external frequency, so first we need to perform the model analysis. Okay. So model analysis is a analysis where we will be predicting the natural frequencies and mode shapes, which will give us an idea about what are the different natural frequencies we have and what are the different mode shapes for each natural frequency. And in each natural frequency, what is the mass participation factor? In which direction mass involvement is more? And what is so based upon that, maybe we can initially predict if there is any resonance or not. Okay, even without performing the vibration sensing. But okay, so but we'll be performing the model analysis and we will be predicting the natural frequencies. And after that, based upon the kind of vibration that our system is exposed. So majorly all the vibrations will be classified into three types. One is harmonic analysis. So harmonic analysis basically is nothing but whenever we have any rotating equipment and if there is any unbalanced force in the rotating equipment which will cause the vibration to the system. Okay. So suppose if you take any motor or pump or any rotating equipment. So when the motor is running with some RPM, if there is any unbalanced force, so that unbalanced force will give some vibration to the supporting mechanisms or supporting structures. Okay. So the kind of vibration that a mechanism or a structure will be exposed because of the rotating equipment will be sincerely very low. Okay. So the vibration that the systems will be experiencing will be varying like a sine wave. You can see this here. So these kind of vibrations generally we will be observing because of the unbalanced force in rotating equipment. So for this kind of source of vibration. So if the source of vibration is any rotating equipment, then we will go with the harmonic analysis. So first we will perform the model analysis, then we will couple the model analysis with harmonics. Okay. Or if we are having like the source of vibration is because of some earthquake or wind loading conditions or some shock or impact and loading conditions. So then we will go with the response spectrum analysis. So basically here we will be having a data. Okay, so the kind of data that we will be having here is initially the vibration, if we are getting like displacement versus time or velocity versus time or acceleration versus time. So this kind of vibrations if our geometry is experiencing. So usually we will be converting this data with frequency versus displacement or frequency versus acceleration or velocity, this kind of data, and we will be considering that as a response spectrum analysis. Okay. So in case if the source of vibration will be having multiple amplitudes, okay, means if the data is too much complex, then like suppose this is the data, vibration data we will be getting. Like the source of vibration may be when the vehicle is moving on the road, or if we launch any rocket, like the thrust or the outside air, like atmospheric air that will be putting the pressure on the uh, launching vehicle. Okay. So if this kind of vibration, if we are getting, usually we will convert this data into a power spectral density. So the second case that we discussed is basically very simple vibrations where we will be measuring the frequency versus displacement. Okay. But if the amplitudes are very high, then we will go with, okay. So if the amplitudes are very high, then we will go with the power spectral density method and we will be analyzing if there is any probability of the failure because of these external frequencies and natural frequencies. Okay. So these are the different vibration, three different vibration analysis that we will be having. And the other type of dynamics that we have is transient analysis. Okay. So transient analysis is nothing but the time depending analysis. Okay.
कौन से ईयर की बात है?
Just a second.
अभी बहुत अच्छा था फिर। मेरे को मेरा पहला अपॉइंटमेंट था, हालांकि 500 ही था, लेकिन
So if you have any questions, I recommend you can put it in your chat box. Put it in the chat box. Let's try. So these are the different dynamic analysis that we have. So usually we will perform the model analysis to predict the natural frequencies and the corresponding mode shapes. Okay. So if the source of vibration is a sensitively varying excitations, like usually the vibrations that we generally expect from a rotating equipment. Okay, we'll go with the harmonic analysis. So here we will be checking the resonance if there is any interaction of the external frequencies and the natural frequencies. And similarly, we will perform the spectrum analysis in case if our source of vibration is not very complex and if it is a time varying uh, vibrations, like usually that will be converted into amplitude versus frequency. So if we are having very complex vibrations where we having multiple amplitudes, then we will go with the PSD approach. And so these are the three different vibrations that we have. And so another dynamic analysis that we will be having is transient analysis. Transient analysis is nothing but the time varying loads. So the mechanism may be working, or if the load is varying with respect to time. Okay. So anything which is varying, which is with respect to time. Okay. So yeah, so these are the different dynamic analysis that we will be having. And so again, the transient analysis we'll be considering into three different approaches. Okay. So especially when we are working on any mechanism, so if our interest is just to check the kinematic behavior of the mechanism, like how the mechanism is working, whether is the mechanism is going to lock because of some over constraints, or you want to see the joint reactions, like the forces at the joints, or the moment or the torque it is required. Okay, so here basically we will be considering all the geometries. So whatever the parts that we have in our assembly, all the parts we will be considering as a rigid parts. So if this is our goal, then we will go with the rigid dynamics. Okay. So another kind of approach is flexible dynamics. So flexible dynamics is nothing but where we will be, suppose you have some 5 or 6 components in our assembly. Okay. So this in our assembly, if you are having 5 or 6 components, so if our objective is to check the kinematic behavior of that mechanism, and along with that kinematic behavior, you want to take the stress or strain or the deformation, like whether it is a compressive or tensile deformation when the mechanism is working. Okay. So suppose if you see this robotic arm, if this robotic arm is picking some load and placing some load, like loading and unloading conditions, if that is the working environment of this robotic arm. So during that operation, like what will be the stress or strain or deformation at any few components? So that might be a single component, or if you want to take more components. So if our objective is a combination of flexible and rigid parts, but here mostly most of the parts, if you want to consider as a flexible parts. Okay. So you can go with the flexible dynamics or transient dynamics, where our goal is to determine the motion, like the kinematic behavior or the forces, joint movement, torque, and along with that, if you want to see the stress strain deformation. Okay, so this kind of others, but this flexible dynamic approach we will prefer when the mechanism is not having high degrees of freedom, and also usually it will take bit more time to solve the problem. So the solution time will be little longer compared to the rigid dynamics. And also, if the mechanism degrees of freedom is too high, like if the rotations are very high, or if the mechanism is going with very high RPM, so it will take a lot of time to solve the problem. So this is one approach that we will be going with. And the latest solver that we have is Ansys Motion. You can say which is a combination of rigid dynamics and flexible dynamics. Okay. So here also we will be checking the kinematic behavior of the mechanism, and if you want to determine the stress strain deformation, all these results by considering the material properties. So which includes both linear material properties and nonlinear material properties. Okay. So but here our interest is more into the motion analysis or the kinematic behavior. Along with that, we will be considering a few parts. So in the flexible dynamics, we can consider most of the parts as a flexible parts. But here we'll be considering few parts, like maybe two parts or three parts, not most, like not more number of components we don't consider here as a flexible parts. Okay. And motion is a solver. If in our mechanisms, if you have any contacts, it can easily deal the contacts, which is having the highly nonlinearity as well. So this is the third approach that we'll be going with, which is a combination of rigid and flexible parts, where our interest is to perform the kinematic behavior along with the flexible results as well. But in the rigid dynamics, okay. So in the rigid dynamics, usually we will consider all the parts as a rigid parts. In the transient analysis, we can consider most of the parts as flexible parts. And in Ansys motion, we can consider both rigid and flexible parts, but rigid parts will be more compared to the flexible parts. Okay. So here in the rigid dynamics, we will not be considering any material properties except the density. Or if you want to consider any CMS part, then we can give the material properties up to elastic limit. But in both transient structural and Ansys motion, we can consider the material nonlinearity as well. Like if you want to include the elastic properties and plasticity properties as well, along with some any hyperelastic materials, if you want to use, you can use it. But in Ansys motion, there is limited material nonlinearity out there. But in transient, we can consider all type of material nonlinearities. Okay. So so along, so I'll give you three to four slides more about the motion analysis to understand better what kind of simulations usually we perform here. Okay. So so like this, the motion analysis will help us to predict the kinematic behavior along with uh, along with the strength analysis of the components which is there in the assembly. And so motion analysis is not only just a multi-body dynamic solver. Even if you want to perform the strength or fatigue or NVH analysis, heat transfer, FMA, FMU, and along with that, it has advanced toolkits. Okay, so these advanced toolkits help us to perform the multi-body dynamic within few hours. So usually, if you want to create a geometries like tracks, chains or belts. So this kind of links, or even if you want to create gears, bearings, shafts. So these geometries you don't need to create in the CAD. Okay. Just a minute. Okay, so like this kind of any parts like shafts, bearings, gears, if you want to create, like you don't need to create this kind of parts in CAD, which is a traditional way. So you can generate all these kind of components within solver itself. Like you can directly give the properties and automatically it will generate different type of gears. No? Okay, so along with that, in case if you want to perform the dynamic behavior of car models, like by considering a path holes or all type of road conditions to check the stability of the vehicles. So you can go with the car a toolkit as well, and easy flex in order to solve the problem faster way without going with complex mesh. You can go with these toolkits as well. So in this particular demo, I will solve one multi-body dynamics problems, and I will showcase the drivetrain toolkit as well. If you want to create any mechanisms with predefined geometries, like by creating the geometries in the motion solver itself, how you will be creating the geometries, I will showcase that one. So yeah, so typical problems that we'll be solving is like we can solve the multi-body dynamics in Ansys motion, and along with that we can check the strength of the components. Like in this case, you can see this geometry. So usually this is the original one that we have, which is having some failure. Okay, at this particular location. So this is the high stress location, and there is a failure here. So you can see in the physical prototype as well. So you can create multiple designs, and you can see that the thickness variation is there for different designs over here. So case 1, case 2, case 3 with varying thickness. And again, when we perform the analysis with different designs, we can pick the best one. So case 3 is the best one where the stresses are very less. So like that, in case if you want to perform analysis for bearings, gears. Okay, so during the dynamic condition. So when the rotation is happening, or like with respect to like with some RPM, if the mechanism is running, during that condition, if you want to analyze and you want to predict the failures or stresses strains in this particular thing, you can do that. So not only single components, even we can go with a big assembly with multiple gears, shafts, bearings, and all, and you can predict if there is any failure like gear wear or gear fatigue. Okay, so at different tools and all, so, and we can check the performance. And yeah, so this is one more case related to the CV joint, the strength analysis of the CV joint. Or if you want to simulate the complete mechanism, and when the mechanism is working, you want to analyze the forces that are required. Especially in this system, we are going with the hydraulic system with integrated of fluid mechanisms. So how much amount of pressure it need to withstand, or like what is the displacement of the hydraulic system it needed. Okay, so like that, we can integrate motion solver with multiple things to go for the complete vehicle. Okay. So even if you want to perform the behavior of the road by considering the irregularities of the road by giving the like path holes or some obstacles. So how the mechanism is working if you are designing a robot or the mechanism. And during that simulation, you want to see the joint reaction forces or the strength of any few components if you want to check, like you can perform all these kind of behaviors. So yeah, when it comes to automotive, like even we can perform the KNC like kinematics and compliance or ride and handling by considering the different dynamic analysis for the steering mechanisms and yeah, okay. So damping and all is complete analysis we can do. So let's start with the live demo. So I will showcase this excavator assembly. Like basically, this is a multi-body dynamic problem. If the excavator is working to pick the load, like loading and unloading conditions. So during that loading and unloading conditions, you want to see the joint reactions or forces or the stress or strain or any other results in any one of the components if you want to analyze like how the mechanism is working and how the kinematic behavior of this mechanism with respect to time. And along with that, we can check the strength of the components of the few parts. So this is the first problem that we will be solving. And later on, we will. Okay. So later on, I will showcase the Drivetrain toolkit as well as per our agenda. Okay. So in Ansys, whatever the problem that we want to solve. Okay. So in Ansys, whatever the problem you want to solve, you can solve all these structural and fluid problems by using the Ansys workbench. Okay. So like once we open the new workbench, basically here we will be having different kind of analysis here. Like we discussed, if you want to perform, maybe I will open new workbench. Okay, so whatever the analysis system, the analysis we want to perform, like we discussed, so like strength analysis, in strength analysis, like static analysis or vibrations or multi-body dynamics or explicit dynamics. Okay, so like that, whatever the analysis we want to perform, so all analysis will be performed in a single platform, that is Workbench. So you can take multiple analysis in a single platform, like okay. Okay, so this is a new Workbench that we have. So here, if you want to perform the static analysis, you can take static structural, or you want to go with the dynamics and you want to perform vibration analysis. So you can go with the modal analysis to predict the natural frequencies or harmonic response if we are having any unbalanced rotating equipment. Okay. Or response spectrum and random vibrations based upon the spectrum data that we have. So this is static analysis and these are the vibration analysis we have. And when it comes to multi-body dynamics, if you want to consider all the parts as rigid parts, then we can go with the rigid dynamics. Or you want all, like most of the parts as the flexible parts, then you can go with the transient structural. Okay. Or we can go with Ansys motion, which is advanced, where we can use multiple algorithms to give the inputs, like if you want to write your own equations like step function or if function to give output or input, you can use all these things in Ansys motion. So similarly, explicit dynamics, like any explicit events, car crash, bullet impact, explosion. So all these kind of problems also we can solve by using the explicit dynamics, by using explicit or LS So whatever the problem that we want to solve in structure, so basically there will be total 7 steps. So to complete the simulation in structures, there will be total 7 steps. Okay, so I already considered the Ansys motion. So to complete the simulations, we need to do the 7 steps. So first one is selecting the analysis system. Okay, so based upon our project and based upon our problem statement, we need to know whether our project will fall under static analysis or dynamic analysis. Again, in the dynamic analysis, whether the problem is related to the vibrations or like some mechanism or some transient problem or explicit problem. So like that, we need to know what is our problem statement and what kind of conditions it's going to withstand. And based upon that, we need to pick the analysis system. So that is the first step. And the second step is engineering data. So if our assembly is having 5 components and one component is made up of steel, another component is made up of some polyethylene or hyperelastic material or copper or aluminum. So like that, if each component is made up of different materials, so all that material information we will be providing in the engineering data. And in the third step, we will create the geometry. And in the fourth step, we will give the connections. We'll create the meshing if it is a flexible body. Okay. Or if it is having an assembly, we will give the connections. We will assign the materials. And in the setup, we will apply the loads and boundary conditions. And we will go with multiple time steps, sub steps, and all in the solution. And we'll pick the solver and we'll solve the problem. And we will check the results. So these are the 7 steps that we have. So in Workbench, we will be completing these first 3 steps, picking the analysis system, taking the material information, and creating the geometry or importing the geometry. Then we will go with the model. So this model, setup, solution, results. So these all 4 steps will be completed in a new window, that is mechanical window. So if we know how to solve a problem in any one of the analysis, so if you are familiar with any one of the analysis system here, you can easily solve the other problems as well. So the only difference between one analysis system to another analysis system is the kind of inputs that we will be providing will be different, and the concept it is taking will be different. But the workflow, the GUI is same in all the problems. So here it is starting the mechanical. Okay, so the mechanical window is open. So once we double click on the model, this new mechanical window will come. Okay, so this is our assembly. Yeah. Okay, so this is our assembly and this is the workflow that we need to follow to complete the simulation. Like we discussed, the fourth step is model, fifth step is setup, solution, and result. So these are the four steps that we'll be completing here. Okay. So this is our assembly. Let's see what is our assembly. So basically, this excavator will be as we all see, we will be watching multiple JCBs and excavator. So this is a part of that JCB excavator subassembly. So usually, if it is picking some load, so if some soil is there here, so the mechanism will work and it will pick the soil and it will unload. So we are going to perform this loading and unloading condition of the soil in this particular simulation. So here, if you see, there will be multiple components. Let me show you the complete assembly. Okay, so these are the different components that we have here. Okay. So these are the different components we have. So this is one part, bucket, and some cover is there. And here we have the hydraulic mechanism, like hydraulic piston and cylinder assembly. So this is the cylinder and this is the hydraulic piston. So there are three hydraulic pistons to activate the mechanism. So you can see this is one hydraulic system. This is second hydraulic system. And here we have the third one. And here we have the bucket. Yeah, so this is our assembly. We have multiple components over here. Okay. So if I click on the plus symbol in front of the geometry, so these are the different components that we have. So you can see whatever the components I can see here, these are the components. So whatever I select in this window, the details will be shown in this tabular data. So suppose if I click on this bucket or cylinder, so you can see this is the cylinder component. That is rod and this is boom and this is swing tower piece and these are some pins connecting rods, crank, okay, boom cylinder. So like that, there will be multiple components we have here. So whatever the component that I will select. So if I select any one of the component, okay. So the details of the component will be shown in this window. So you can check what is the material that we have assigned, whether the behavior is rigid or flexible. So rigid means there will not be any stress strain deformation, but it will showcase the mechanism. Like it is it will do the kinematic behavior analysis, but it will not give the stress strain deformation. Okay. So what is the material that we are using for that component, and what are the dimensions, bounding box properties, like, and what is the volume of the selected geometry, mass, centroids, and okay. So these are the complete details of the selected geometry. So yeah, so this is the core like materials that we have selected. Like you can see the material properties or the coordinate systems, okay, and the remote points. Okay, and these are the connections. So basically, in multibody dynamics, connection plays a major role to get more accurate results. So there will be multiple type of connections are available. Like if you right click on connections, so here we have contacts, joints, and spring connection. Or in strength analysis, we will be getting the welded joint, bearing joint. So like that kind of different connections will be there. So maybe I will give some overview about the contacts, or the basic difference between the contacts and different type of joints. Okay. So all like most of the connections are classified into contacts and joints. So the basic difference between a contact and a joint is contact will not be having any fixed degrees of freedom. Okay. So if I insert a manual contact, so here I have total 5 type of contacts usually in analysis. Okay, so bonded, no separation, frictionless, and frictional. So there will be one more contact in another analysis, that is rough. Okay, so total 5 will be there, but in motion it will be having only 4. Okay, so there will be 5 type of contacts. So these contacts will not be having any fixed degrees of freedom, but usually we will be selecting the contacts by using two things. One is sliding and another one is, yeah, so tangential behavior, that is sliding, and another one is separation. So based upon these two, we'll select which type of contact we need to go with. So based upon the tangential behavior, that is sliding. Okay. And another one is normal behavior, that is separation. So bonded means, suppose if there are two surfaces which will be in contact, if you consider the both contacts, both surfaces as a bonded contact, so it is like a fixed. So with respect to one surface, another surface will not move in normal direction. That is, it will not separate and it will not slide as well. So sliding is also not allowed and separation is also not allowed in terms of bonded contact. Okay. So no separation means these two surfaces will not separate, means there will not be any gap allowed between the surfaces, but it can slide. So only sliding is allowed. For example, if you take your mouse and table, okay, so between the bottom surface of the mouse and top surface of the table, if I consider as a bonded means like fixed. I can't move my mouse, like I can't slide my mouse, or I can't separate, like I can't take the mouse out of the table. So that is bonded. No separation means I can like I can slide my mouse over the table, like I can slide, but I can't separate. I can't take my mouse out of the table. Okay. So again, frictionless means I can slide my mouse. So sliding is allowed, and separation is also allowed. Like if I want to take my mouse from the table and keep it in my bag, I can keep. So frictionless and friction are same. Both will be having sliding and separation, but the only difference is friction will be having a additional force which will be stopping the geometry to move further based upon the frictional coefficient. But for the frictional coefficient is 0. Okay. So if the frictional coefficient is 0, that is frictionless. If the frictional in real world application, most of the things are frictional. So if you are having a frictional coefficient in between 0 to 1, you can go with the frictional. Rough means the frictional coefficient will be very high, that is 1. That means because of the high friction, if I try to move my mouse over the table, whatever the force that I will apply to slide, that complete force will be opposed by the frictional force. So the sliding is not allowed because of the high friction, but it can be taken from the table. Okay. So these are the 5 contacts that we have. Based upon the separation and sliding, we can stick for our application whether we want to go with the bonded or frictionless or frictional or this kind of contacts we can select. So like that we can insert and you can select two surfaces. Here in this mechanism we are not using any contacts, but I will just show you. Suppose this is one phase and this is another phase. So between these two phases you can go with bonded. Bonded means it is completely fixed. No separation means sliding is allowed, but separation is not possible. So similarly frictionless and frictional. Okay. So like this you can create a contact. So in this mechanism, we don't need any contacts, so I'm deleting these contacts. And another type is joints. Okay, so there will be multiple type of joints. So the contacts will not be having any fixed degrees of freedom, but the joints will be having fixed degrees of freedom. Okay, so once I insert the joint, so here in my screen, we can see translation along X, Y, Z, rotation along X, rotation Y, rotation Z. So for each and every joint, there will be 6 degrees of freedom. That is 3 translations, translation along X, Y, Z, and rotation. That is rotation along X, rotation Y, rotation Z. So I created most of the joints, but for our understanding, I will create few joints here. Okay. So suppose these are the two components that are connected. So this geometry and this geometry are connected over here. So if I want to move this geometry with respect to this like this. Okay. So if it is like I want to create a revolute joint, so here I can select a revolute joint. Okay. So like you can select what type of joint you want to create between body to body. Like if it is a fixed means completely not movable in any one of the degrees of freedom. So revolute joint means rotation along Z axis is allowed. If I go with cylindrical joint, rotation along Z axis and translation along Z axis is allowed. So translation means translation along X. Okay, universal joint, spherical joint. So whatever the joint that I have selected, based upon the joint, it will be having a degrees of freedom. So rotation allowed X, Y, Z, but translations are not allowed in the spherical joint. So similarly, planar joint, in a single plane, the rotation is allowed and also translation along X, Y, Z is allowed. So like that, we can select any one of the joints. So suppose I selected a revolute joint between these two. So I will showcase in the presentation as well, like how these mechanisms will work. So suppose this is a revolute joint. So you can see rotation is allowed, like only rotation is allowed. This is a revolute joint, and this is translation joint. Sorry, cylindrical joint. Both rotation and translation is allowed, and this is translation, pure translation. There is no rotation. Okay, and this is a slot joint. Okay, and universal joint. So these joints we see every day in different kind of applications, and this is spherical joint. Okay, and this is planar joint and bush joint. Okay, so like that, we need to select which type of joint we need. So in this case, I am selecting a revolute joint. Revolute joint means rotation along Z axis is allowed. So I am going to create a revolute joint between these two parts. So I will select this face as a reference. So with respect to this face, this geometry is moving. So this is one face. This is another face. Okay, so this is a joint between these two parts, and it is only allowed to move in rotation Z. You can see a coordinate system. So this is the Z axis. So it is allowed to rotate only in the Z axis. Okay. So similarly, let me create these two joints as well. So let me insert one more joint and we'll make it as a revolute. And so I will consider. Okay. So these two phases as a reference, and this phase and this phase as a mobile. So here we need to select two things, reference and mobile. So mobile means moving body with respect to some phase. So this is a reference. With respect to reference, the other geometry is moving. Okay, I'm inserting one more joint, and this one also I will make it as a revolute, and this will be my reference. Okay. This phase and this phase. So this is my reference. And this will be my mobile part. Okay, so I have created three revolute joints here. You can see. So between this part, so this is a revolute joint between these two parts, and between these two parts, one more revolute joint, and between these two parts, one more revolute joint. Okay. So similarly, I will create one more translation joint. So I will insert one more joint, and this one I will consider as a translation. So translation means it can move only in x direction. So translation along x-axis. So I will select the inside face of this one for translation. And this face as a mobile. So with respect to the cylinder, this piston will move in x direction. Okay, you can see the coordinate system. So with respect to with respect to this cylinder, this piston will be moving in the x direction. Okay. So yeah, so let me insert the one more final joint, that is body to ground fixed. Means this geometry I'm fixing to other geometry, but other geometry is not there with me. So I'm considering that as a ground. So I'm fixing this with respect to ground. So body to ground, and it is fixed. So all degrees of freedom are restricted for this geometry. Okay, so like that, I have created all the joints. So this is a translation joint between this piston and cylinder, and revolute joints, revolute. Okay, so I already created all these different joints for the complete assembly. So like once I create all the joints, now I need to apply the conditions, like boundary conditions, loads and boundary conditions. So I am going to apply the four boundary conditions. So one is, I want this geometry to rotate like this, and this piston and cylinder hydraulic pistons. So these three hydraulic pistons, I want to give the rotations. So first, let me give rotation input to these two geometries. So between these two geometries, I need to give the rotation. Okay. So let me right click, insert joint. So this is the joint. So in this particular joint, I want to give the condition. So I'm going with the joint boundary condition. Okay. So here, basically, I am solving this problem for a duration of 10 seconds. So let me give. Okay. So this is yeah. Okay, I'm solving this problem for a duration of 10 seconds. So let's take, this is time, and this is rotation. Okay, this is R. Let me consider this as a rotation. So total, I am solving this problem for 10 seconds. So this particular joint, so the joint between these two components, I don't want to rotate this geometry, this geometry with respect to this geometry up to up to 6 seconds. So the first 6 seconds, it will be, suppose this is 6, this is time. So the first 6 seconds, it will be constant. So this I will consider as a 0 for the rotation. So it will be, I don't want that geometry to rotate up to 6th second. Okay. And once it will reach to 6th second, I want it to rotate in negative direction from 0 to pi by 4. So 0 to pi by 4 radians. So I want that to rotate from 0 to, so this I will consider as radians. Okay. So I want this geometry to rotate from 0 to 8. So this will be 8. And again, once it will reach 8, there I don't want to move it further. So this is my condition that I want to apply to this problem. So to this one. So I will select this joint. Let me go and check what is the joint here we have. I will just rename it as R so that I will not be having any confusion. So this is so I just rename it as R. So this is the joint R. So here I will select that joint R. and I want, like, I can give the moment or initial conditions like radians. If it is a constant, I will go with it. But I want in some particular fashion from 0 to 6 seconds there is no rotation. From 6 to 8 seconds it need to move from, okay, so it need to move from 0 radians to 5/4. So this one. So that is why what I will do, I will go with function expression. So I will write my own function, and this one is rotation. So I will write my own function. So let me go to motion sub-entity and I will write a function. Okay. So here the first point is, so this is the first point that we have. So basically time is 6. So in bracket I will write it as 6 seconds, 0 radians, and this one is at 8th second, 5/4 radians. So these are the 2 points that I will give in my function. So from 6, 0, that is 6 seconds, 0 radians, at 5 seconds, 5/4. So this curve I will give. So but it is in negative direction. So basically it is in negative direction. So I will give minus. So I will write one function minus step time 6, 0. So that 6, 0. Okay. So 6, 0. So that 6, is 0 is nothing but this point. Okay, so 6, 0 is this point. And another one is 8, 5/4. Okay, so the second point is this one. Okay, so these are the 2 points I have mentioned here. So this one I will apply here. So I will select the function expression. Okay, so this is the function expression I have given for this 2 geometry. So this will rotate, this will rotate, this will rotate with respect to this. From 6 to 8 seconds, the rotation is 0 to 5/4 in negative direction. Since I have mentioned a negative, like minus value. So similar kind of motion function expressions I have created here. So this is one function expression. So you can see I have included step 0 to 2 seconds, it will 0 to 40, and again minus 6 to 8, it is 0 to 40, and again minus 8 to 10 seconds, it is 0 to 50. So like that I have mentioned 3 functions here. So these 3 I will give to my cylinders. So there are 3 hydraulic systems are available. Okay, so I will give all the 3 to all these things. So what I will do, I will insert 3 joint load conditions. So this is one joint load properties. Again, I will insert one more joint load properties, and again joint load properties. So these 3 joint load properties are for these 3 piston and cylinder assemblies, like the hydraulic system. So the first one is, you can see translation joint, geometry 9 is there. First I will select this one, geometry 7. The geometry 7, this part between these 2, function expression and motion 1. Okay, I have assigned one function between these, and similarly I will take one more, and I will assign for this, and one more, and for this also I will assign motion 3. So 4 inputs I am providing. So 4 joint load properties. One, that is rotation here, and translation between these 2, and again translation between these 2, and the translation between these 2, these geometries. Okay. So here I am solving this problem for a duration of 10 seconds. So you can see end time is 10 seconds. And okay, maybe I can go and solve the problem. Okay, so I'm solving the problem. It is solving right now. So if I consider all the components as a rigid parts, so you can see all the parts I considered as a rigid parts. It will not take much time to solve the problem. So let me showcase you how the mechanism is running. So it is solved. So within few minutes, like within 1 or 2 minutes, the problem will solve and it will give the results. Okay, so you can see the mechanism is working. Okay, so from 0 to 6 seconds, it is not rotating. Now it will rotate. From 6 to 8 seconds, it is rotating 5 by 4 radians. And these three, okay, and these three hydraulic systems is also working as per the input that I have provided here. Okay, so during this mechanism, in case if you want to calculate any joint reaction or any loading conditions like that, you can select that. Let me evaluate this. So you can see 11 Newton because as of now, I didn't provide any soil load here. So I didn't provide any soil load in the bucket. And I didn't consider the standard earth gravity also. So because of that, you can see like these are the reaction forces along X, Y, Z. So in the tabular dot also I will get X, Y, Z. Or in case if I want to go with total movement. So movement along X, Y, Z and all. Okay, you can see this is the moment. So like that, whatever the result that I want to take out. So like any forces or moment or torque along X, Y, Z, something like that. So all this kind of output I can consider as a like I can take out from this simulation. Okay. So now I will show you one more thing. Yeah. So I have solved the same problem once again, but here I consider two geometries as a flexible parts. Okay, you can see here. Let me. Okay, so you can see basically here this geometry, and this geometry, and this geometry. So three geometries I changed from, and one more thing, this one also. So these all geometries I changed from rigid body to flexible body. And once I solve the problem, now I can see the stress values as well. So you can see maximum I'm getting 61 megapascal in this region as a stress. And here I will get the graph as well. Okay, so during that mechanism, like I have applied the bucket load here. So bucket load also I have applied in this bucket. So you can see in this area I have applied the bucket load also with using the function expression. So this is like from 6 to 8 second minus 1000 Newton load. And again, from 8 to 10 second, it is unloading. So minus 1000 to 1000 means it is 0. So 1000 Newton load, it is taking from this location to that location like that. Okay. So when this load is acting and when the mechanism is working, so even if I want to take out the stress values also in any one of the parts, so you can see maximum stress here. And these are the stress values with respect to time. Okay, so like that, we can check the mechanism, like how the mechanism is working. So this problem usually it will take 1 hour or something like that to solve the problem, since it is having the flexible bodies. But only with the rigid bodies, we can solve the problem within few minutes, like 1 or 2 minutes, and you can see how the mechanism is working. And you want to take out any joint loads or moment or any force or something like that, you can take out as a. Okay, so like that, all the rigid parts also you can consider, and also flexible part also you can consider, and you can check the deformation, stress values, the major point at the stress values. So this is a graph from 0 to 10 seconds. What is the stress? So the maximum stress is 61 megapascal at 8th second. Okay. So because the 8th second is the unloading condition, so okay, so here we can see at 8th second. Okay, so here we can see at 8th second is 61 point. Okay, this one 61, around 61 is there. Okay, so like that we can check, but I don't have the animation here. If I want to solve again, it will take a lot of time actually. Need some animation. Yeah, so I need to solve again, but it will take a lot of time. So I'm just showcasing the directive. So the same problem you can make it as a flexible body and you can solve it. Okay. So this is how we can solve the multi-body dynamics. You can see the mechanisms and you can get the stress values, deformations and everything in any one of the part. And along with that, if you want to take out any joint reactions while rotating, so like while the mechanism is working during the time, so what is the joint reaction in that particular thing, like the force, moments. So all these results we can take it as output. Okay, so yeah, within 5-10 minutes, I will try to showcase you about the generation of geometries by using the toolkit. Let me take a new motion and here. Okay. So here I will take a new geometry for the drive kit. Okay, basically it is a carrier assembly, and inside the carrier I want to I want to generate some planetary mechanism like okay, planetary gear set and ring gears, these kind of geometries if I want to create. So I will show you like how you will be creating the geometries without going in the CAD. Okay, so let it open new mechanical window. So it is loading. Basically, I have two carriers now, and inside the carriers, I need to generate. Suppose I want to create the planetary gear system. Okay, so you can see these are the two carrier geometries I have. Okay, it's still loading. Yes. So this is my assembly. Initially, I have only two components you can see here. So only two components I have. And so suppose inside this, okay. So inside this, I want to create a planetary gear set with one sun gear and four pin irons. Okay. And here also, I want to create one more gear set with one sun gear and three pin irons. So one, two, three pin irons. And here I want to create four pin irons with one sun gear and one ring gear each. Okay. So like that kind of gearing or some components if you want to create the geometries and again to assemble and to create the connections between them, it will take a lot of time. So in these situations, we can use these toolkits. Like I told, we have four toolkits: Drivetrain to create the geometries, or links to create the connections, and car toolkit basically uh, for riding and handling and kinematics and compliance. So this kind of stability analysis of the four-wheeler, if you want to create, you can go with this. So in this, if I go to drivetrain tool, you can see these are the different geometries I have. So if I want to create any geometries, I can directly select here. So suppose I want to create two planetary gear sets in one particular location. So that is inside this and inside this, I want to create two planetary gear sets. So first, let me insert coordinate systems here, the location where I want to create. So I'm inserting one coordinate system, and the location of the coordinate system is origin, like the origin. So this is one. Okay, so this is the location where I want to create the planetary gear sets with four pinions. I will insert one more coordinate system, and here I want to create at x equal to 0, y equal to 50, and z equal to 0. So this is another location. Okay, so once I create the coordinate systems, the location where I want to create the gear sets, let's go with motion, toolkit, and planetary gear set. Okay, so here just we need to provide the information about the like planetary gear set that we are going to create. So okay, so what is like how many, what type of gear you want? Like suppose I want to go with a helical, right? Okay, and helix angle, I want to go with some 8 degrees. Okay, and so you can see model, I will go with 1.6. So this is the information about the planetary gear set. Oh, okay. And yeah, pressure angle, if you want to define, you can define. And along with that, how many number of pinions. So I want 3 pinions at one end and 4 pinions at one other end. So I will make it as 4. This one, first one. Okay, so 4 pinions, and so let's define the properties of the sun. So this is normal definition, and so you can see this is sun gear, and so this is pinion and ring gear. So sun gear, pinion, and ring gear. So this information we need to provide. So suppose on the sun gear, I want the number of teeth to be 48. So 48 teeth I want on sun gear with face width of 50 mm. And addendum coefficient, I will give it as 1, and this one addendum 1.25. And profile shape, let's make it as minus 0.2. Okay, and tool tip radius, I will keep the default. Okay, that is fine. And similarly, in the pinion also, I want the number of teeth to be 24. And face width, I will go with 32. Okay, face width 32. And addendum coefficient, dedendum coefficient. Okay, and profile shape, let's make 0. So these are the properties of pinion, and similarly the ring gear as well. So the ring gear I want minus 96, which is inside the ring gear. So the number of teeth should be minus 96 with the same face width of the pinions, that is 32. And so the profile shift also I will make as per the pinion. So like that, you can provide a number of pinions you want to create. Okay. And what is the face width? What are the dimensions of the pinion, like face width, number of teeth, radius, and all? Like this, you can create planetary gear set. Okay, and let me duplicate it. And the planetary gear set 2, I will just do few modifications. So one is I want number of pinions to be 3. Okay, so this one is number of pinions should be 3. And let me give some random initial angle 0.849, like that. Okay, so here let's make face width of the sun gear also 32, and the remaining all I will keep as it is 32, 32. So like that, I have mentioned the properties of the two planetary gear sets. Okay, let me create the carrier concept carrier as well. So here I will select the location where I want to create the first gear set. Okay, I created one coordinate system. So this one, this is the location of, okay, first one, first planetary gear set, and this is the coordinate system. Okay. This is the coordinate system for planetary 2. So in the concept carrier, let me take the first coordinate system. Okay, so pinion shaft length also I can give it as 32 and pinion shaft diameter 14. Okay, and here planetary gear set first one I created. And the distance between the sun gear and pinion will give us 48. Carrier board I will not use. So let me insert one more concept carrier. So this one also I will give the same properties, like I want this to be 38, 14, and planetary gear set 38. Okay, so like that I basically I created these two and I mentioned the location of them, in which location I want to create. Okay, now let me just what I will do, I will go to the geometry, and these two geometries I have. I will make it as transparent. Okay, so I will make these two geometries as a transparent so that if I create new geometries, I can see. So first I will create this geometry, planetary gear set 1. Just I need to right click on it and click on create geometry. So once I click on create geometry, automatically the geometry is like whatever the shaft and pinion I have properties I have provided. So the complete assembly will be generated in that particular location I defined. Okay, so you can see now like the geometries are adding here in this tree, and it is showing the status of progress, overall progress. So it is just going on. Within 1 minute, I can see the planetary gear set with 4 pinions, 1 wing gear, and 1 sun gear. This drivetrain will help us to create these kind of gears and all. And once it will create the gears and all, and it will generate the connections between them as well. So if we have this information, then usually we'll apply loads and boundary conditions as in the previous model. You can see here, once I click on this concept carrier and click on create geometry. So as per the dimensions I have provided, it created one sun gear. Okay, so we have one sun gear punans and one ring gear is also there with us. Okay, and you no need to create a joints or any conditions between them, because you can see here in the connections. So all joints. So you can see revolute joint between these two parts. Okay, and again the here. So all joints will be automatically created between them. So in order to create the definitions of them, you just mention the properties, and once you give the properties, you just select the position, like in which coordinate system you want to create these gears. So the first you need to provide the properties, and you need to provide the location to create the geometries and some dimensions, like what is the shaft length of the pin and diameters. Okay, and sun gate to pin and position. So this geometrical properties, if you provide, it will create the geometries and it will give the results like that. Okay. So usually if you want to create the same kind of model by using the CAD and do the assembly, okay, so it will take a lot of time. So in order to avoid that time, you can use this drivetrain toolkits, which will help us to create the geometries by within few steps. All these different geometries here we can see bearings, different type of gears, okay, and housing shafts. Shafts also we can create with the different sections, like the dimensions and all. Okay, so this is what we discussed. We went through different type of dynamics and different type of solvers like transient, rigid dynamics, motion, and contact and joint definitions, and one demonstration, live demonstration, and motion toolkit overview, and we just see the setup and created the setup. So in case anyone have any doubts, now we will discuss.